Hello, my name is Emery Hill, and I will be presenting my bar magnet lab. So to start with the introduction, the purpose of the lab is to observe and measure the distance dependence of the magnetic field due to a bar magnet, comparing it to a predicted distance dependence calculated using equations on and off-axis magnetic fields. And for a quick preview of the results down there, we have our n and mu values there, which we'll get into later. So to recognize some physics principles at work here, we have, most importantly, I'd say the Biot-Savart law, which is right here, and it describes how constant electric currents create magnetic fields. It gives the relationships for that. And two other ones that were important for this lab. Sorry, this picture is a little bit blurry, but we have the magnetic field represented through a dipole formation, right? It's the model created by dipole style. Um, and then the distance dependence formula, which is specific to this lab. Um, that's why it was particularly important. It describes the relationship between distance and B field. Here's a quick picture of the glow script code. Sorry, the bottom arrow I think is cut off in this, but you can see the off-axis and on-axis arrows, and then that 45-degree arrow of the magnetic field. This was created in GlowScript. This is the model. To recognize the system, surroundings, and initial conditions, well, here's an image of the system. It's missing the magnet is off picture here because it was pretty far off from the phone. But this is the surroundings, and the system is going to be the magnet. Everything else is part of the surroundings. And for the initial conditions, there aren't really any for this lab. I would just say um, to make sure our initial conditions were right, we had to zero the magnetic field. I say zero, I mean account for Earth magnetic field, the magnetic north. So we had to change some values on the phone for that. Besides that, there's no other conditions. For a quick overview of the procedure, like I just said, the magnetometer, which was the phone, was adjusted to account for Earth's field. Data was recorded based on the instructions, off axis, on axis, everything, and entered into the spreadsheet. The dipole moment and other values were determined from the data. They were calculated. We'll get into that in a bit. And then a computational model was created. Here's a preview of some code and the model right there um, to make calculations for the distance and visualize everything and the arrows. And then it, gave me the final results. So here's the code in GlowScript. I've color coded everything here. This was all the important things I changed. So we have like yellow is most of our constants that I was putting in. The green is, our dipole function right there. Um, these are our vectors off axis, on axis, the distances, really. That's just the distances of where the arrows are. Red are uh, some of those arrows. Um, and then blue is more of the arrows. These are different locations. And then the gray over here is a lot of the outputs, and we have our 45-degree arrow there. For the main results, you can see the values right here of all of the on and off axis arrows, the 45-degree and the distance. And uh, we'll get into the numbers on the next slide here. So the computational model predicted a value of around 1.846 e negative 5 Tesla, while the calculated value was around 6.422 e negative 5. So they're both in the same order of magnitude, so I'd say it's pretty successful. The difference is probably due to, inevitable imperfections between real life and computations. It's important to address in the experiment also that we assume the bar magnet acted like a magnetic dipole, allowing us to use the Biot-Savart law. It's also important to recognize that we did not account for other forces, which in reality there would be. So that causes some of that difference. Final questions. What if you hadn't oriented your experiment to compensate for magnetic north? Well, the values would just be a little less accurate overall. And that's really all. And then what if you were to stick two magnets together? Magnets together. The second one would just cause everything to double, assuming you put it in the same orientation as the first one, and the arrows would all say the same direction. Besides that, nothing would change, just the magnetic field would double. For some potential errors, well, these two right here are magnetometer errors. They're possible if it's a failed instrument or it's not adjusted right. That can cause issues. And then obviously measurement error. If we don't measure perfectly while using it, that can cause errors as well. Thank you for listening.